iMathAS, an automated assessment of mathematical proof by Melanie Platz, Ingo Dahn, and support of Ulrike Dreyer. Outline. First of all, we give a brief overview what is iMathAS. Then we look on the requirements and constraints of an eProof environment. The next step is to look at the structure of an electronic proof. Then we look at the authoring support within the iMathAS environment. What does the automatic assessment could do, and where is manual assessment additionally needed? And finally, we draw some conclusions and look on next steps which are optional for the further development.
So what is iMathAS? iMathAS is a web-based internet mathematics assessment system which you can use within a browser. It has an integrated computer algebra system which is not visible for the user. It has a gradebook, so automatic grading is possible for mathematical homework and tests, and also for electronic assessment. The questions are automatically generated, and the numerical and math expression answers can be graded by the computer, but it's also the option of free text and essay environments where you need manual grading of the teacher. iMathAS allows an accurate display of math and graphs. A randomizer function allows individual questions for all students. They are structural equivalent, so they have to solve a matrix, but the question has different values for all students, so that cannot copy and paste a result. They have to calculate the task on their own. The biggest benefit for the author is a joint shared repository between all authors and teachers, and the questions can be provided to the community. You can keep the questions in a private library, and you can take questions from others, modify them, and integrate them into your private library. On the other hand, every teacher also can provide good questions to the community so that the community can use the questions in their tests and in learning environments. Now we look on the requirements and constraints of the application. So what are the requirements and constraints? First of all, it should be open source so that we can minimize the financial constraints of the application. Most educational organizations have limitations of available money, so a core installation, for us it's provided for Rhineland-Palatinate, is provided for all universities so that they have a joint repository of resources which they can use. It should have a collaborative support so that the participating institutions and universities can share their work between the authors. The next step, we need to provide an individualization for the students so that every student could get an individual task for all students that can be automatically generated. The next step, it should include a help system and tutorial environment to adjust the level of support to the learner and according to their problem-solving skills. And the last step, which is highly relevant for the eProof environment, it should be possible to integrate an electronic proof by copy and paste into a task environment which is provided by the web-based mathematical assessment system. Now we look on the basic structure of an electronic proof as is used in this context. First of all, we look on the structure of an electronic proof, and in the definition we use in this presentation. There's a landscape of different proofs, and we classify the eProofs just in between the understanding of a given proof on one side. Everything is fixed. You go through the step and try to understand every step in the proof. There's no option for you to modify the structure of a proof, add comments, add justifications. On the other hand, you have a white piece of paper and you create your own proof for a given theorem. The electronic proof is somewhere in between the understanding of a given proof or creating your own proof. It has some kinds of options where the students can select fragments of a proof, order them, provide different pass to the conclusion that is possible within the eProof, but is not as flexible as a white piece of paper and not so rigid as a given proof in a textbook, for example. The solution of a student is checked against the correct solution, which can include different pathways from the preconditions to the conclusions. On this slide we see two correct solutions starting from the precondition and ending at one conclusion. The second correct solution has a different proof steps in between and starts also with a blue dot inside from the precondition and ends with at the conclusion with the blue circle. So if we combine both correct solutions into one solution graph, the solution provided by the students is checked against the solution graph. So now we look into more detail of the structure of the electronic proof, and we will provide the semantics of the edges and vertices in the solution graph. First of all, the proof can be decomposed into single fragments. And second, each fragment consists of more or less three components. First is the connection to the previous fragment. This connection to the previous fragment is identified with the vertex in the solution graph. The second is the description of the fragment itself. So you have an attribute which explains what is the node in the solution graph used for. And third, there could be a list of justification for a proof step going from one node to another. On this slide you see the students review in iMathAS. It's just a screenshot from the browser Firefox, and you see that all mathematical symbols are displayed correctly. The upper part of the web-based environment is providing the theorem that the students should prove. You see that the mathematical symbols are displayed correctly in the browser. The next part in the student's view in iMathAS are the proof step the students has already provided in the eProof environment. And the last part visible on the slide are the input area where the students can select predefined proof fragments, can select the connection to the previous proof step, can reorder the fragments in the proof, and can provide justification for a certain proof step. Going back to that image of a given proof and a white piece of paper where you can create your own proof, the eProof environment is just in between. But if you want to facilitate or give the options to the students that the students can define their own proof step and use them in the eProof environment, there is an option available in which the students can type in their own proof step in an editor. Here's just a small example. Provide an ID for the proof step, and by creating a reference to this proof step with the ID, the proof step is integrated in the list of the proof fragments. And you need, of course, a justification for the introduced proof step if the justifications are available in the system. If you provide the option of own proof step in the given eProof environment, this leads to the consequence that the teacher needs manual correction for the electronic solution provided by the student. Nevertheless, other proof step might be graded correctly by the already given graph of the solution by the teacher. But it is recommended to look into the graph if it's logically correct. In the following slides, you will see a mixture of predefined and self-defined proof steps. The first one is self-defined, then you have two selected proof steps which are given by the teacher's environment, and then the fourth proof step with ID my2 is also a self-defined proof step with a text fragment introduced in the eProof environment. Now we look at the authoring support within the eProof environment provided in iMathAS. This means the author should not know the syntactical correct iMath Vintex to provide the graph solution. He just should be able to click through the environment and create the iMathAS code syntax by going through the proof and provide a correct proof from the preconditions to the conclusions. In the middle you see a code fragment of the solution graph, how it should be implemented in iMathAS. It is not acceptable that a teacher or author has to deal with the course syntax of a solution graph, so it should be possible by clicking and using the available and defined proof fragments in the proof and connect them to a logical system of proofs from precondition to conclusion. These clicking in the web interface should create the source code of the solution graph. And this is what the eProof environment provides to the user. They create a logical proof step in the web interface, and that is reproducing the student's activity in front of iMathAS as they should solve the problem. You can create different paths from A to B, from the preconditions to the solution, and you combine the available proof step in the solution graph. Then the only thing the iMathAS teacher or tutor has to do is to copy and paste the generated solution code into the eProof definition, and then the student solution will be checked against this solution graph. The solution graph is from the syntax very close to PHP programming, so it is not necessary to know much about PHP. You have to copy and paste it to a certain position in the eProof definition of the theorem. Now we have a quick look on the assessment, especially the automated assessment in comparison to manual assessment of self-defined proof fragments. So here you see a mixture of self-defined and predefined proof steps. The two predefined proof steps cannot be automatically assessed or graded by the eProof environment, and in the automated assessment it says manual assessment for this proof step. The second proof step is part of the solution graph, and so it can be automatically generated and just test if all justification for the proof step are available in the system. And then the third proof step is again a self-defined proof step which needs manual correction. The conclusions. First of all, we use an open source environment, iMathAS, which is installed for all universities and educational settings in Rhineland-Palatinate. This is the good opportunity is to have joint collaboration on a joint repository, so that a provided task can be adapted, modified to the individual needs of universities, and learn from good practice, good case studies of tasks which are used in lectures. The third thing is the individualization of proofs. The randomizer is allowed to provide the individual tasks. This is a side effect of using iMathAS in lectures, and so that students cannot copy and paste the solution from one task to another, because they have to solve their own task. And so you can see what student is capable to solve that task, and who student were not able to solve the task. There is an integrated help system in iMathAS, which we don't discuss in this proof, but it is available, so you can have different levels of help. When more and more errors occur, you can provide more detailed helps to support the learner. And it is possible to integrate the eProof environment to iMathAS by a copy and paste solution. And you copy the programming environment into the iMathAS editor mode, and you just have to add the proof fragments into the system and click through the provided solution graph and copy and paste it into the editor environment for the teacher or tutor that uses the iMathAS environment. We provide the flexibility to introduce self-defined proof step and use predefined proof steps. At least we have reached a technological solution that provides an option in between those two pillars, understanding a given proof and create your own proof step on a white piece of paper. So far, we have just reached a technological solution to provide option in between understanding a given proof and creating your own proof on a white piece of paper. So the core question is still, does the eProof environment support the skills of logical deduction of a proof? Provide more opportunities, learn the skills of proving and deduction more quickly, more efficiently, then provide more deep understanding of a proof. Though this is unanswered questions, and the objective is the learner should be supported in to be able in the long run to create their own proof on the blank piece of paper. And the supportive mechanism of an eProof environment has still the need of an empirical study. How and why should it used in an electronic environment? Last but not least, I want to thank Dr. Ingo Dahn, Melanie Platz, and Ulrike Dreyer for supporting this concept in the last year. And thank you very much. And I will be available for questions in the Flash meeting.